Okay, well, thanks very much for inviting me and for this awesome program. And thank you, everybody, for sticking it out to the end of today. A long, hard day of lots of algorithms and cryptanalysis. So, yes, I will be telling you about how Diffie-Hellman fails in practice. So this talk will be much more practical than some of the rest of today, mostly because we're going to be talking about deployed crypto. And this is a collaboration done with a very large number of people. I have had many people ask, how did this happen? How could you possibly have an author list with 15 authors? It's partly because this is about 3 or 4 papers shoved into one. And so that might make more sense. And there's like 6 different research groups represented here who do many different things. So it's a long story, but I can tell it to you later if you want. Also, like, this is kind of a diverse audience, and this is like a little bit further away from what some of you guys do. So if stuff doesn't make sense, just like ask lots of questions, because that's a lot more entertaining for me. So good, okay. So I'm going to go like way back to, I don't know, the origin of modern cryptography. This is like the mathematics of modern cryptography. So maybe this is like the paper that started modern cryptography. I don't know. These people are a lot older now. But hopefully we've all read this, and we've all taught classes where we have like slides like this, and given papers or given talks where you have slides like this. I put this here mostly to contrast this. Ooh. Now I have a voice. Okay. I put this here mostly to contrast sort of the Alice and Bob key exchange with what you'll see later. So this is like this nice theoretical version of Diffie-Hellman key exchange, nice and clear. Alice and Bob send G to the A, G to the B, and then they have a shared secret, and then they can communicate with each other. Looks clean, looks clear. There's only 2 arrows here. And I will be specializing to the case where we have a multiplicative group, mod P, in this talk. So nothing about elliptic curves, no more exotic groups, just multiplicative groups, mod P. So, okay. And fortunately, yesterday, Daniela introduced a lot of this background for me. So I will just quickly sort of resume some of this just to get us in the mood. So we have a prime, which is some parameter specified from on high. We'll talk about where those come from later. Then there's a generator of some multiplicative group, mod that prime. And we know that, well, for Mod's little theorem, okay, so the group order is maybe p-1, maybe something else. And then we know that the order of the group will divide whatever p-1 is. So, and the discrete log problem, which we care about mostly because it will help us break Diffie-Hellman in practice, or DSA, digital signature algorithm, is given some value g to the L, compute this log L. Okay, so we have a target, we have a log, we try to compute that. And we know that this log is some value mod the order of g, which is some value that divides p-1. So I'm going to just go through the whole history of discrete log very quickly in one slide. So the best algorithms for generic groups run in time of square root of the order of your group. Pollard row, baby step, giant step, depending on how much memory you want to spend. If you have some size range that you know that your exponent or your log value lies in, then you can compute the log in times square root of that size range. And if you know the prime factorization of your group order, then you can compute a discrete log in each of the prime subgroups, and then use the Chinese remainder theorem to compute the log in the whole subgroup, okay? So Daniela talked a lot about this. Hopefully you guys have all taught this, seen this before. We're all good. Okay, so these, I mean, we've known about these algorithms for decades, centuries, decades maybe. So fortunately in practice, people design the parameters so that these algorithms do not apply. This is not why you're here for this talk, to see me tell you about like Pollard row, right? And so the best practice is that when you're giving real-life Diffie-Hellman parameters, your group generator should generate some large prime order subgroup, mod P. And so common choices are safe primes, where P is, say, 2 times some prime plus 1, so that you have as large of a subgroup as possible. Or a DSA group, which is designed so that p-1 has some large prime factor q, which is not say, p-1/2, but is something much smaller, say 160 bits or 256 bits or whatever, that's specified as part of the group parameters. So these are the two sort of examples to keep in mind in practice of what these groups look like, or what they should look like. So, pop quiz. How many people think that practitioners deploying cryptography follow the best practice? Who wants to vote yes? Who wants to vote no? All right. Right. If I'm giving a talk, okay, you know what the answer is. Okay. It might maybe be better than you think. So here's some concrete numbers. So I will talk some more about HTTPS later, but we scanned the entire internet, connect to every single server, say, hello, do you speak HTTPS? It's the encrypted web, the little lock on your browser, and got back an answer. So of those, so there were 14.3 million hosts that were willing to speak to us over HTTPS, and of those 24% spoke Diffie-Hellman. So that's reasonable. It's actually a much larger percentage of the websites that you actually want to talk to support Diffie-Hellman. The rest of them support RSA key exchange, if you're wondering.
Is that both elliptic curve Diffie-Hellman and traditional?
This is only mod P Diffie-Hellman. Elliptic curve Diffie-Hellman is about 10%, or it was the last time I looked. I can give you a reference if you want the actual number. But elliptic curve is much lower still. And actually, this number is much higher in the websites that you care about visiting, mostly because in recent years, people have been saying, oh my God, everybody needs to move to forward secret key exchange methods because we're being spied on by the NSA. So there's actually been an increase in support for Diffie-Hellman and elliptic curve Diffie-Hellman key exchange.
So when was this number from?
What is this number?
When did you get this number?
This number is from like April.
And you're saying that it's higher now than it was?
No, this is the number from April. This number is much higher than it was in, say, 2010. Okay. So of these, whatever, 3-point-something million key exchanges, we actually had 70,000 distinct primes. So there are a lot of people using the same prime values, which is fine. I mean, we don't really have that much guidance on how to choose primes, as Daniela was pointing out. So there's actually, if you look at the distribution, it's like a really long-tailed distribution. There are a few prime values that are really, really, really common, and then there's a long tail of people who generate their own values.
What are those common values? The ones, the really used ones?
The really used ones, the most commonly used ones were generated by, say, Apache and OpenSSL. And groups like that, and just, if you install some common server software, it just will come with some prime baked in often. There are also a few groups that were generated in the 90s. They're called the Oakley groups. So there's a 768-bit prime, a 1024-bit prime, a 1536-bit prime, all the way up to, I don't know, 4,000, 8,000 bits, with nice properties like having 2 as a generator, being a safe prime, having 2 generate a subgroup of order p-1/2, having the most and least significant bits be all set to 1, having most of the intermediate bits be a nothing up my sleeve value, which is, I think, the binary expansion of pi, and then they increment to, the next prime that has all the properties that I just listed. And these were published in 98, something like that. And people have been using them and baking them into protocols ever since.
Because I don't know anything about HTTPS. So if I'm talking to one of those servers and he says, here's a prime I like, and I say, I don't like that one, let's use this one, then
You can't do that.
I see.
The server just says, here's my group parameters.
I see. So the client has no control over what's going on.
Yeah, depending on the protocol, sometimes the client chooses the parameters, sometimes the server chooses the parameters. I have a whole slide that goes through the key exchange later on, but I'm doing the mathy bit first. Okay. So, in this case, the servers are choosing the primes, and you don't get any input in what they look like. So the servers, that's how many primes we saw. Of those, we looked for, how many of these are safe primes? And the answer is most of them, actually. So there are a few that are not safe primes. And a priori, since we only get a prime and a generator, it's hard to tell the difference between a non-safe prime and a non-safe prime with other problems or a DSA group, because we're not given the group order to check. So we decided to check whether these were DSA groups or not, or whether there were additional problems. So we tried to factor p-1/2 using the elliptic curve method, which is your preferred method if you want to find small factors of numbers. And of those, we learned prime factors of the order of the group generator for 750 groups. So at least 750, well, so many tens of thousands of people using these 750 primes messed up, and we're using...
All prime factors or some prime factors?
We learned some prime factors. Not all, but this means that these are not DSA groups and that these are not safe primes. So these people have problems.
By safe prime, you just mean that property. It doesn't mean that...
Safe means that p-1/2 is prime, yeah.
So, yeah, it's not that the other primes shouldn't be used because they're not safe. So.
It's fine to use a DSA prime, or a DSA group, for example. You just want to be sure that, best practice is you know what your subgroup is and it has large prime order. So these people have subgroups that have composite order that we were able to factor just by, on a few hundred cores, applying the elliptic curve method for several thousand moduli for I think I just pressed go and let it run for 5 days. So,
Were any of those the popular ones?
some of them are used by tens of thousands of hosts, which is moderately but not super popular.
So any of the primes happen to be smooth or p-1?
Yes. Okay, so is this a problem? Well, it certainly breaks the DDH assumption if we've got a key exchange of this form, but it's not actually a vulnerability in practice immediately, because if somebody just wasn't paying attention to the kind of primes that they were generating and they just generated some random prime and didn't check if it was safe or DSA or anything, then p-1 is likely to have large prime factors. And so if we have an exponent that we're trying to recover, well, we need to, if we were going to try to do it with Polig-Hellman, we might have to solve discrete log over mod, say, something of 300 or 500 bits, which is just not feasible. So this is not a priori a full-on break vulnerability.
What's a DSA prime?
DSA means, so DSA primes, as specified by the digital signature algorithm specification, just say that p-1 should have a large known prime order subgroup, and G will generate this prime order subgroup and nothing else.
So these seemingly vulnerable, G will generate that subgroup. So
G just generates that subgroup.
What you discovered is that this could not possibly be a DSA prime.
Yeah, these are not, these 750 are not DSA.
Or even if the prime is DSA, G it doesn't.
G does not generate the right subgroup, yeah. So these are people who definitely screwed up. Yeah?
So given that the safe scope happens for many, many connections, is it because this was embedded in some software then it got used over and over again?
Mm-hmm.
What software? What software?
We did disclosure to a bunch of different companies. I'm not sure what the situation is with that. The final version of the paper will contain some example implementations. There are some devices, and there are some cases where we're not sure, actually, is one of the difficulties.
Are these mostly proprietary or open source libraries?
I don't know if we found any source code, but we didn't look that hard. There were at least 10 different things that did 10 distinct different things that did this, 10 distinct implementations where we could tell these all come from one implementation, these all come from another implementation.
But, so they were open source or they weren't?
I didn't find any source code, but I didn't look, so I don't know.
So this was a problem more with with the order of G than the factorization of p-1.
Mm-hmm.
P was fine, but then they were choosing a G that does not have prime order.
Yeah. Most of them just say, 2 or 5, that sounds like a good generator. And I'm guessing a lot of these people just said, I'm going to generate a random prime, and I'm going to take 2 mod that prime.
Isn't it enough for G to have the order of G to have a large prime factor to get security?
I'm going to go on to the next slide, and then the answer is sometimes yes, sometimes no. So if you have full-size exponents and you have a large prime factor of your group order, then you can't recover that full-size exponent. But there's a paper of Van Oorschot and Wiener from the 90s, which pointed out, in theory, that there was this possible attack if instead of using full-size Diffie-Hellman exponents, you used short Diffie-Hellman exponents. So because exponentiation is relatively expensive, doing a, say, 1024-bit exponentiation might be more than you're willing to spend, and you say, okay, well, the best generic attack against exponents within a certain range for discrete log is to use Pollard lambda. So we're going to use, say, 160-bit exponents that has 2 to the 80 security. We're totally good. Now, if you combine this with having a composite order group that is being generated by G, then if you can find a set of small primes where their product adds up to larger than your known size of the exponent, then you just need to do the Chinese remainder theorem for that set of primes, and then you recover the full exponent. You don't have to bother with these pesky 300-digit primes. You can only focus on the small ones, and then you win. So the question that we asked is, did anybody manage to both combine having short exponents and having a composite order group that they were generating?
Yes.
Good job. So we ran this for just sort of prioritized all of the exchanges that we had in order of the most effort that we would have to use to break them. The smallest effort was like, I don't know, 30-something bits, and then we got up to 40-something bits of security, so like 80-bit primes, 80-ish bit primes. And using that, we got 159 full exchanges, so people who actually were using 128 and 160-bit exponents, and then some people who are using larger exponents than that. Okay. This is like a somewhat small diversion. But this is an example of why applying a small amount of math knowledge to the internet is interesting. It's a little bit like shooting fish in a barrel. I've learned that if you scan the internet and you look for implementations that have screwed something up, you will find it. So, and the most interesting reason that this seemed to happen, actually, is because of a usability problem with DSA keys. So there are some very commonly used DSA parameters. People say, here's a well-known good DSA group. It's specified. Here's a prime, here's a group order, and here's a generator. And some people were somehow using the group order as the generator, which is going to be just some random number mod p, which is going to generate a random-ish subgroup mod p minus 1. So anyway, I thought this was entertaining. Now you're all like pumped up for discrete logs, right? So let's move on to more modern algorithms. Pollard row is old. Let's talk about some sub-exponential algorithms. So I'm going to explain sort of the big picture of how index calculus works. So, okay, we're trying to solve a discrete log. We've heard the word b-smooth before. So an integer is b-smooth if all of its prime factors are less than some bound b, which is our smoothness bound. And in the slides that follow, there's just going to be magic b that comes out of the sky. So the sort of general structure of index calculus looks something like this. This is a little bit different from what you've seen, but I'm trying to build up to the number field sieve, so you can pretend that like this is the algebraic side and this is the rational side. Anyway, so step number 1 in index calculus is we are going to find a bunch of relations. And a relation is just a pair of integers that are equal mod p and that are both b-smooth. So we are going to enumerate integers. We're going to try to factor both of them or write down their prime factorizations. And if the prime factorizations are b-smooth, then we save them. And we do this until we get enough relations. These are called sieving algorithms because usually you use some kind of sieve to actually discover the prime factorization. So once we have generated a bunch of relations, well, what are we actually doing here? I can write out each relation here, and I've just taken the log of both sides. So I've moved from a product to a sum, and so I've got some kind of whatever these exponents are, and the logs of all of these small primes, which I don't know what the log of these small primes mod p is, but I want to solve for it. So now I have a bunch of linear relations in terms of these logs of small primes. And I also potentially get some relations for free, depending on what the group is. And once I get, so I have, say, b unknowns here. And I have, once I get more than b relations, then I can solve this system of linear equations, mod the order of the group that I'm working over. And then I get the logs of each of these small primes inside of sort of mod p. So then I've done all this work. I've computed the logs of many small primes, but I still don't actually have the log of the actual target that I was trying to get. So I'm going to input a target t. If my target, if I try to factor it over the integers, if it's already b-smooth, then I am done, because then I can just write down the prime factorization of my target, and then I can write down what the exponents are, and I can substitute in what my known logs of each of the small primes, and then I'm done. But if we're not lucky and t is not b-smooth, then we have to do a little bit more work. And the extra work that you can do is, say, try to find some value. We just try random values here until we find some value, say, g to the r times the target that happens to be b-smooth. And if I find a value like that, then I can just write down what the log of the target is in terms of my known, my known value here and the known logs of each of the small primes, which I have derived in the previous step. So just the sort of general structure of this algorithm is we have a pre-computation, which is relation finding and linear algebra, and then we have the actual part where we compute the log of a particular target. So what does the running time look like? The running time of relation collection depends on a bunch of parameters, the amount of work that it requires to test if your integer is b-smooth, the probability that a random integer of a particular size is b-smooth, and then whatever this value b is. The linear algebra runtime depends on the cost of doing sparse linear algebra for some b-dimensional matrix, mod the order of your group. And the individual log, this depends on the probability that somehow you can find some new modified target that is b-smooth. So if you optimize for what the right value of b is, you get a sub-exponential running time. So it has this L notation. So it's exponential in some constant factor, which here is square root of 2 plus little of 1. And then it is square root of log p log p. So that's this 1/2 here. This is an L of 1/2 algorithm. I'm going to gloss over sort of the differences with the number field sieve. Mostly for our purposes here, there's this extra new step in the beginning, which is polynomial selection. So the property that we want is just to find some integer m and some polynomial f such that f of m is 0 mod p. This will define some number field that we'll be working over. And then we have a ring homomorphism between the ring of integers inside of our number field and then z mod pz. So then we're going to sort of do this same relation collection inside of the number field and then over the integers. So here on this side, I have my ring homomorphism. I have values a plus b alpha inside of the number field. If this is a smooth element of the number field, it factors into small prime ideals. And I'm massively waving my hands here. So somehow you have to believe me that it's possible to figure out what smooth prime ideals are. Essentially you factor the norms and you throw in a few other things to make sure that you're dealing with well-formed ideals. And then here in the integers, we're just factoring relatively small integers here. So I collect a bunch of relations of this form. Then I do a linear algebra step to solve for the logs of the small elements inside of the number field and the small elements in the integers. And then once I've done this step, then there's a last step, which is the descent step, which is trying to write an individual target as the sum of the logs in our known database. And then if you work through the parameters here, you get a slightly improved runtime. So now I have massively, yeah?
How much of this process is shared between, like, if you were going to use the number field sieve to factor? I mean, is this is most of the algorithm the same?
It's very, very, very similar. So almost all the code is the same. So for discrete so polynomial selection, so for factoring, you essentially have the same property that you want, except that for p, instead of p here, you have some integer n. That's the thing you're trying to factor. Relation collection is very similar. You have to do a little bit more work to deal with making sure you're something about your ideals being well formed. And then linear algebra, the big difference here between this and factoring is when you're doing the number field sieve for factoring, your linear algebra is mod 2. And here it's mod the order of your subgroup. And then in the number field sieve for factoring, you don't have a descent phase. You have a sort of final square root phase at the end. So this is much more expensive than the final square root phase. But otherwise, the structure of the algorithm is very similar, and the expensive parts, the relation collection and the linear algebra, are very, very similar. So this is sort of a picture of what the number field sieve looks like if you're sort of actually thinking about implementing it. So here's the runtime that you get. It's L of 1/3 for the pre-computation step with 1.9 as the constant in the exponent, and L of 1/3 with a 1.2 constant in the exponent for the descent. So this part only depends on the prime p actually. And this is the only step that actually depends on an individual target. And I've tried to draw a little picture of what steps parallelize well and what steps don't. So polynomial selection and sieving, they're embarrassingly parallel. You can distribute them as much as you want. It doesn't matter. Linear algebra can be somewhat parallelized, but it's more limited because the different steps need to communicate more with each other. And then the descent is somewhat parallelizable, mostly because you're essentially doing a lot of resieving. So if you want some practical numbers of what this looks like, let's see, this is using the CADO NFS implementation of the number field sieve. This is done by our collaborators who are at INRIA and LORIA in France. So for 512-bit factorization, here's some of the parameters that you would use. This is the sieving range, so you would sieve all values a and b up to the 2 to the I. And then this is the large prime bound, so the size of the prime that you're willing to accept beyond the sieving range to save a relation. So the amount of core years of sieving that you would do for a 512-bit factorization is about half a core year. Linear algebra is also less than a year, and then there's no descent. So RSA 512, if you parallelize this can be done in a few hours. For Diffie-Hellman, we've changed the parameters a little bit just to deal with the fact that linear algebra mod your group order, which is a larger number, is much more expensive than linear algebra mod 2. So because of that, that blows up the size of the linear algebra. So these, you can actually do more sieving and make sieving more difficult for you by decreasing the size of your large prime bounds, for example, in order to decrease the size of your matrix to compensate for the fact that you have to do all of your arithmetic mod sum q, which is larger than 2, rather than just mod 2. And then the descent is about 10 minutes of core time. So this gives you some idea of what concretely it means to have L of 1/3 with 1.9 versus L of 1/3 with 1.2. And on an actual cluster, so the sieving was parallelized across 2,000 to 3,000 cores using idle time, so that's why it varies. So this was 15 hours of sieving on 2,000 to 3,000 cores. The linear algebra took 120 hours, so several days on 288 cores. And then the descent, average time of 90 seconds, parallelized across 24 cores. So as far as we know, I don't think anybody had bothered to write down. This is smaller than the current discrete log record, which is about 600 bits, but nobody had ever sort of bothered to write down the case that anybody actually cares about in practice, for whatever reason. Questions? Good? Shocked? Okay. So why do we care about this? Okay, here's my little picture of TLS. This is what the TLS protocol actually looks like. So this is a cartoon of the exchange. So say I want to talk to eeks.berkeley.edu. I looked around for like several minutes. Simons.berkeley.edu does not speak HTTPS. www.berkeley.edu redirects from HTTPS to insecure HTTP. So eeks.berkeley.edu is willing to speak HTTPS to me. So if you are Alice and you want to talk to a website secured with HTTPS and you want to speak Diffie-Hellman, the negotiation looks something like this. So Alice sends over a random value and the list of cipher suites that she's willing to support. So hello, I'm willing to speak RSA key exchange, Diffie-Hellman key exchange, elliptic curve Diffie-Hellman key exchange, whatever. Then the server responds with a random value. It sends over its certificate, which for our purposes, it will contain a public RSA key and a signature from a known trusted authority on that public RSA key. And then it will choose a cipher suite, which for our purposes, it'll say, okay, I would like to speak Diffie-Hellman with you. And it will send over its Diffie-Hellman key exchange value, and it will sign that key exchange value with its RSA public key. Then Alice says, cool, we're speaking Diffie-Hellman. Here's my value g to the b. Now we have a full Diffie-Hellman handshake. We derive some authentication keys and some encryption keys from using our Diffie-Hellman key exchange value and our client and server randoms that we exchanged. And then we exchange max of the full dialogue here, or hopefully the full dialogue, in order to make sure that we both agree on what this handshake looks like using our shared secret that we've derived here. And then Alice sends over, hey, can you send me index.html and the using symmetric encryption, and the website says, here's index.html.
List of ciphers? That includes the list of ciphers or not?
The Mac?
Yeah.
It does not. Or no, wait, it does. Sorry. Yes. This includes the list of ciphers and the chosen cipher.
And it also, it's kind of structural. It includes the G to the A and G to the B.
Yes.
That went through to 3.
Yes.
So,
Yes.
So,
Yeah.
I am lying to you in many places in this slide because this is like a huge cartoon. I mean, you can go read the TLS RFC if you want to be scared for your life. I think it's a good thing for crypto people to do. But yes, so this includes like all of the important things here. So this is okay. So what provides authentication here? We have a sort of sequence of things. We trust the signatures from the certificate authorities because we have their public keys, and we trust their public keys implicitly. The certificate authorities sign the server's Diffie-Hellman value. So this authenticates the server to us. And then the server is sending a MAC of the whole dialogue. So we sort of chain trust that way. And then the encryption is just given by the Diffie-Hellman values, G to the A and G to the B. Of course, there's no authentication of the client, but the server doesn't really care who the client is. You can do this in TLS, but nobody does. So it's kind of like where these guarantees come from in the actual protocol. This is much more complicated than the first slide. Okay, so there's many differences here between practice and theory. There's the negotiation part. There's the politics of what cipher suites we include here. I'm going to talk about this in a second. If you teach a crypto class, you mention Elgamal immediately after Diffie-Hellman, but almost nobody uses Elgamal except for PGP for whatever reason. There's often group negotiation that needs to be built in somewhere. I talked about the short exponents, a choice that seems fine, but comes with some caveats. There's this long-tailed distribution of group parameters, most of which are not known to be vulnerable, but we don't know how to choose groups better than others. Is it good to have everybody use the same groups? Should everybody generate distinct groups? I don't know. And then there's some interesting things, like if you scan for SSH, which we did, and you look at what primes people are using, there are only a few thousand primes used by all, I don't know, 10, 15 million servers supporting SSH. And almost all of them have almost all of their bits in common. So there's, in fact, a list of, SSH, unlike TLS, actually does have a group negotiation protocol. But the group negotiation only negotiates out of a set list of primes, which are basically just starting at a value and incrementing next prime for a little while. So they all share almost all but like the 32 least significant bits in common, which is really odd. I mean, I don't see a vulnerability here, but if somebody wants to think about this, that's something weird, given what I'm going to talk about. Okay, so, boy, I'm like out of time. All right, so does anybody actually use 512-bit Diffie-Hellman? So in the cartoon version, well, okay, so if somebody was dumb enough to, so if a server uses a 512-bit Diffie-Hellman group here, then we know we can just break this offline. We're fine. There are some servers that do this. Most of them are not dumb enough to do this. There are some servers that are still using 256-bit Diffie-Hellman, because 256-bit crypto is secure. Okay, but does anybody use 512-bit Diffie-Hellman? Actually, a lot more servers support 512-bit Diffie-Hellman than you would like, and the reason goes back to, say, the 90s crypto wars. So this is from the ITAR regulations back in the bad old days when cryptography was regulated as a munition. Of course, we are allowed to export cryptography. I am exporting cryptography right now by giving a talk. But cryptography is still on the Commerce Control List of the United States. And you need an export license to export cryptography of any kind of security. Factorization of integers in excess of 512 bits. Discrete logs of larger than 512 bits. This is still active. So
you can export lattice cryptography. That's okay.
I don't know. Discrete logarithms in any group. Well, yeah, I guess it doesn't say any discrete. Yeah, so lattice is good. Okay. You should be careful. It might end up on the list. If you succeed, it will end up on the list. If Chris succeeds, yeah?
Isn't it true, though, that doesn't actually apply to most countries? Or I thought, I read about this a little while ago, and I thought that there was like a list of countries that, some countries on some known bad list that you couldn't export strong crypto to, but like most countries, you can there are actually in practice no export controls.
In practice, there haven't been export rules for a while, although I am not a lawyer and I don't know exactly what the regulations are. If you're like a normal individual human being, you're fine. But I know of researchers who get hassled by their universities over export licenses. Like posting something on the internet is exporting to one of these bad countries. So.
Because universities don't always hire the most competent lawyers.
Well, that is.
It's not the government's fault.
Well, I'm a little bit alarmed by this, to be honest. I mean, especially given all the other crypto war stuff that's going on.
Are you talking about posting code or posting papers with a description of the algorithm?
There's an exemption for research.
Yeah, research is exempted. So if it's a paper, it's okay.
Yeah. Yeah, we haven't had to worry about this in a while. But the artifact that this turned out, this resulted in is back in the bad old days of the 90s, if you wanted to post a version of Netscape online that supported cryptography, it was only allowed to speak, for people who were outside of the United States to download, it was only allowed to speak these export cipher suites. And many servers, I mean, modern browsers don't support these cipher suites. They don't announce, hey, I'm willing to speak export grade cryptography. But many servers never turned off support for these export grade cipher suites. Because what's the harm? A real client is never going to negotiate such a thing, and we wouldn't want to cause any problems for people who never upgraded from Netscape from 1996. So in March 2015, export cipher suites are supported by 36.7% of these 14 million sites, which is surprisingly large. And there was a paper, intersection with our paper is Karthik Bhargavan, which they had several vulnerabilities, but this included the freak attack, which used fast 512-bit factorization to downgrade modern browsers to broken export-grade RSA. This attack relied on multiple things. One of them was a implementation flaw in almost everybody's TLS implementations, where a man in the middle could just send an unexpected message to the server, and the server would just not notice that it was unexpected and instead negotiate broken export-grade crypto. And if you figured out what their current key of the day or week was and factored in advance in a few hours on EC2, as one can do, then the man in the middle can then just use the factorization to forge the MAC of the handshake, using as if everybody had negotiated the cipher suites they expected to, and then it will just go through. So that was an implementation flaw. So then one of the things that we did in this paper is extend this idea to Diffie-Hellman. Yeah?
So that meant that, let's say that I'm trying to connect via TLS to, I don't know, to Berkeley, and the man in the middle intercepts it, and now they have a key with me or with the server?
They are able to, they now have your shared secret. So they have downgraded your connection to export-grade cryptography, so they can compute both of the encryption and the MAC keys, and then they can start injecting whatever they want into the connection.
Don't they need to break it on the fly? To forge the MAC?
So they need to do a 512-bit factorization, but actually all of the implementations only generate a 512-bit key when they start up. And then they use that key until the next time the server is rebooted. And so if a server stays online for a few days or a few weeks, as they do, then you have a few days or weeks in order to factor this key. So then you could say, well, what happens with Diffie-Hellman? Well, back, if you think that 512-bit Diffie-Hellman has the same amount of security as a 512-bit RSA key exchange, unlike generating ephemeral export RSA keys, servers actually do generate a new ephemeral export Diffie-Hellman exchange every time they get a connection. So you would have to break the discrete log in real time. And if it cost as much as a 512-bit factorization for each of these, then such a downgrade attack would not be possible. But because we can do a pre-computation for a prime and then do the online computation for an actual target much, much faster, that means that that a downgrade attack of this form actually is possible.
Wait, that's if the prime is smooth? I mean, the B-1 is smooth?
No, that's in general for 512-bit. So that's using the number field sieve implementation numbers that I gave with a 90-second-ish online cost to compute an individual discrete log, if you know the prime in advance.
How critical is it to switch this red stuff from Diffie-Hellman export to Diffie-Hellman exchange?
So this is a somewhat confusing diagram of the downgrade attack. So the client says, I'm a modern client. I speak normal Diffie-Hellman key exchange. I definitely don't speak Diffie-Hellman export. The man in the middle replaces all of the perfectly good cipher suites that the client is willing to speak with, I only speak Diffie-Hellman export. Hello, I'm Mosaic from the 90s. And the server says, OK, fine, I speak Diffie-Hellman export. Here's my key exchange values, and here's a signature of my key exchange, which includes all the parameters, but not the Diffie-Hellman export. And so the man in the middle passes this through, and the client just thinks that the server speaks normal Diffie-Hellman, but with a 512-bit group. It can't tell the difference between Diffie-Hellman, downgraded Diffie-Hellman export and Diffie-Hellman, normal Diffie-Hellman with a 512-bit group.
Downgraded means that you just use a short exponent, or sorry?
Downgraded means it uses a 512-bit P prime.
So then why can't I tell? I can see that the prime is short.
But some people use normal Diffie-Hellman with a 512-bit prime. So.
But that's effectively the same.
Yeah. Well, yeah. Except that this server might say, I'm going to be safe. I'm going to use a 2048-bit prime, but I'm going to keep I'm going to keep export on because nobody normal would negotiate this with me, and I want to make sure I can get all the customers I have. So the effect of this downgrade attack is to keep the client from, it's to cause a client who's connecting to a server that they would normally have perfectly good security with, to downgrade it to bad security if the server is willing to negotiate broken crypto with people who only speak broken crypto.
Are the Macs no longer part of the picture here?
The Macs are so the Macs are part of the picture. So there's a signature. We can't forge the signature because this is with a full-size RSA key. So the rest of the key exchange goes through. Now, in order for the man in the middle to convince the client that everything has gone okay, it needs to compute this MAC. And in order to compute this MAC, it needs to figure out what the MAC key was. And in order to figure out what the MAC key is, it needs to compute the discrete log of the downgraded Diffie-Hellman key exchange.
Since you're in export control mode, isn't the MAC key only 40 bits anyway?
It's like, I'm not sure. 40, 56, I don't know. We need to know that it's correct. Yeah, so we need to compute the correct one. So if we just compute the discrete log, then we immediately know what the correct one is, and just send it.
I still don't understand. So you're saying the client is trying to use secure stuff, but the secure stuff is only 512 bits? So I'm just not understanding the difference between this DHE and DHE export if both of them are 512.
So normally, if the man in the middle wasn't here and the client says, I want to speak DHE, the server would say, here's some 2048-bit parameters for you.
Oh, I see. So they lie about parameter. So the client doesn't notice that the prime is really short or something like that.
Yeah. So until our paper, the clients would never alert on 512-bit keys. And
this should be clear to the client who send too short of a prime.
how often do you check? How often do you check what parameters you are being sent?
No, with the software.
Well, but there were so many sites out there that were still speaking 512-bit primes that the browser implementations didn't want to cut it off.
But is this attack at least adding this prime with some leading zeros, or you don't even do that? You send a short string and detect.
You just send a prime. So until our paper.
Would it accept a 50-bit prime?
So at some point, I think most browsers, except a couple, had cut off primes less than 512 bits. But there was sort of this popular conception that doing online 512-bit discrete log was as hard as doing a factorization every time. So it's not, who's going to do that? So this is clearly not a vulnerability.
So if we just signed, instead of what we do sign now, which includes G to the A, or G to the B, if we also signed the list of ciphers, then we'd be done, right?
Yeah, so this is a flaw in the protocol, that the server is not signing its choice of cipher suite.
And also in typical key agreement, or theoretical key agreement, when we don't do a MAC, we use a signature at the end, which also was before.
Yeah, those are more expensive.
Right.
Just to make sure I understand correctly, when the server sends G and G to the B, it thinks that this is a computation over, it interprets this as numbers over 512-bit prime, but the client thinks of G to the A as something over 2000.
No, they both agree on the choice of prime. So the server thinks, oh, this client only speaks this broken crypto, so I'm going to send it a 512-bit prime, and I'm going to send it G to the A mod that 512-bit prime. So the client and the server both agree on what their prime and their generator and everything are. There are other sort of cross-protocol attacks where the client and the server, like the man in the middle, convinces the client to send one kind of key, and the client interprets it as the wrong kind of key. There's some cute attacks of that form also, but this is not that. This is everybody agrees that they're speaking 512-bit discrete or Diffie-Hellman.
Does the client check for primality?
No, clients don't do anything.
So you could send a smooth number, even if it's long. You could send.
You cannot get a signature, right? So you need to forge the certificate from the server, and that will unfortunately include the right prime and the right.
We're not forging any. We're assuming the signature is good.
So the Alice and Ron attacks will not work because, the most trivial attack would be for man in the middle just to send like a 5-bit prime, and then you're saying nobody checks everything, but you're saying it won't pass because of the signature.
Yeah, we can't do that because the server is signing. Yeah.
So when they exchange max of the protocol transcript before the actual encryption, does the MAC also include the cipher suite?
Yes, which is why the man in the middle needs to forge it.
So then the man in the middle needs to compute discrete log online while the client and the server are communicating.
Yes.
So even if it only takes 10 seconds, isn't there like a timeout that would take place, or?
So there's a list of things that you can do in practice. I deleted that slide because I was told to like focus on the math here. So there's, you might say, okay, yeah, 10 seconds is like way longer than a normal person is willing to wait. So things that you could imagine happening, there are all sorts of little ad beacons that get transferred. So like you wouldn't notice if you loaded New York Times and then there was a tiny little ad beacon that took 10 seconds or 90 seconds to load while you were looking at the page. But a man-in-the-middle attacker could then insert some malicious thing instead of that ad beacon onto your page, and you would trust it because it was HTTPS. Another example is if you were doing HTTPS over some offline client, like you just had a web script that was downloading things, then the script is not going to notice if it takes an extra 10 seconds to connect to a page, probably. Then there are a few other, you can send like keep alive messages that will delay the finish message timeout until the attacker has time to compute the discrete log.
So given like a choice of an ephemeral exponent for Diffie-Hellman, this only needs to be done, does this need to be done per connection or per new choice of ephemeral exponent?
Per new choice of ephemeral exponent.
So like if a web server is up for a week and it's using the same ephemeral exponent for the entire time, then it just has to do this once, and then every client is pwned, basically.
Yes.
Will the server actually use the same ephemeral exponent? I mean, why not choose new one?
For exponent grade crypto, the servers were using a new exponent every time they were connected to. For non-export grade Diffie-Hellman, ephemeral means I generate one when I boot up, and then I use that same one forever until the next time I'm rebooted.
That is still an option? That's still happening?
That is the way that many servers operate. I think Apache does this.
But are there servers that are using export grade crypto and also not generating a new exponent for?
Not that we saw. I think, or maybe only a tiny handful. So the vast majority of these guys were generating a new ephemeral exponent for every connection for export, but not for the full-size Diffie-Hellman. Right, okay. So carrying out the attack, we need to do pre-computation for the primes. So you can ask how many pre-computations do we need to do to attack everybody on the internet. The most common prime is used by 82% of the servers that supported export-grade crypto. So you get a lot of bang out of your 1 week of computation there. The next most common prime is 10%, and then there's kind of a long tail of distributions again. I had this before, 1 week on each 2,000 to 3,000 cores. The individual descent times, it actually has this sort of nice S-curve. It's kind of a random process how long it takes. I'm embarrassed by this number because it should be less than a minute, but the code is not very well threaded, so this number is larger than it should be. Anyway, maybe we'll improve it. I don't know. Okay, so I'm totally out of time, but I'm going to tell you about the politically more interesting part of this paper. I guess if you want to leave, you should leave. But okay, so we've established that many hosts use the same group parameters, and that there's this possibility of a pre-computation attack with much faster online individual discrete logs if everybody's using the same parameters. So what does this say about passive attacks on 768 or 1024-bit Diffie-Hellman, which are very commonly in practice? So here are some numbers for cost estimates of discrete log. We got these in a few different ways. So the current factoring record is 768-bit RSA. This is from late 2009, published in 2010. So here's some sieving ranges and large prime bounds. And this is slightly adjusted from the numbers in their paper. So they did a lot more sieving than they needed to in order to make the linear algebra easier. We backed off a little bit from that. So this is sort of estimated what it would cost using modern hardware, normal computers, CPUs, to do 768-bit factorization if somebody were to repeat that result now. To modify this number for Diffie-Hellman, as I said before, we have this problem that the linear algebra is way more expensive, so we want to do more work in the sieving phase in order to reduce our workload in the linear algebra phase. So there's kind of a limit to how far you can push this. So this number is saying, okay, we do 10 times as much sieving here, and we decrease the size of our matrix somewhat. And still, the linear algebra is like way more expensive. But we did some experiments, and the descent is about 2 core days. So this is, I mean, if you parallelize this, then this is not so bad at all. Then the sort of more interesting question is 1024 bits. It's been sort of a sport, I guess, for cryptographers to say, how expensive is 1024-bit RSA for the past couple of decades, right? So here's some extrapolated parameters sort of from here if you scale things up appropriately. This is about how expensive we expect 1024-bit RSA to be. And correspondingly, if we expect the same-ish approximate benefit from over-sieving and decreasing the size of the matrix, here's about what it would cost. So this is a rather large number. This is not such a large number. This is rather large. And the descent is actually not that bad. So this number, I mean, this was the INRIA people, some experiments with the early abort elliptic curve method. This was published by Dan Bernstein and Tanya Lange, who were talking about doing a batch number field sieve. So this seems to be the best way to do the descent. So with some experiments, we did not run it all the way through, but with some experiments, we guessed that the descent will take about 30 days. So this is about what you expect sort of 1024-bit RSA and Diffie-Hellman to look like now.
Just to be clear, these are core days.
These are core days, yes. So all of these things can be parallelized. This can be parallelized perfectly. This is less so. This is pretty well parallelized. So what does this look like if you have the resources of a government? The best current design for factoring that we found is an ASIC sieving design. This paper is almost 10 years old at this point, so moving to sort of modern designs. The number is quite low, actually $8 million to sieve a 1024-bit discrete log with the 10 times over sieving that we estimate in hardware. But there's a problem with the linear algebra step, which is if you take the largest supercomputer purchased by the NSA, which has 300,000 cores, the linear algebra step would take 117 years. So this is clearly not quite feasible, but it is within a constant factor of feasible, which is what should worry everybody. So if you either assume that there are some smart people out there who have gotten a 100-time improvement, or if you can expect, say, 80 times speed up for doing linear algebra in hardware, special purpose hardware, this would cost hundreds of millions of dollars, but this is not out of range. It is so close to in range that this should clearly be retired. Okay. Now is where it gets more exciting. Okay, so I don't know how many of you read this article. There was an article in 2012 by James Bamford talking about large breakthroughs that the NSA made. This is pre-Snowden, by the way. The NSA made an enormous breakthrough several years ago in its ability to cryptanalyze or break unfathomably complex encryption systems employed not only by governments around the world, but also many average computer users in the US. They were thinking that this computing breakthrough was going to give them the ability to crack current public encryption. And in the rest of this article, I've cut this out, he sort of alludes to, he thinks it's AES. But I don't know about you. I read this and I said, this doesn't sound like AES. This sounds like, I don't know, 1024-bit RSA, maybe. That was my speculation. I think the next slide, if you have a clearance, avert your eyes. So this is from the Snowden leaks, a brief quote from the 2013 NSA Black Budget. We are investing in groundbreaking cryptanalytic capabilities to defeat adversarial cryptography and exploit internet traffic. So they're making it very clear that they are doing something online to the internet right now.
What do you mean by adversarial cryptography?
You guys? All right, keep averting your eyes if you have a clearance. So this is from one of the Snowden leaks. This is a slide about decryption of VPN traffic. So this is sort of out of context. Can we decrypt the VPN traffic? If the answer is no, then explain how to turn it into a yes. If the answer is yes, then this is my favorite slide from the leaks ever. Happy to. I mean, I feel this way when I decrypt things too. But this gives some information. I mean, most of the Snowden leaks, there hasn't really been a lot about cryptography, to be honest. Like, there's not much, like, technical things in there. We find out about, like, kind of what the capabilities are. There's some, like, numbers. But really, the only sort of cryptographically interesting thing in there has been what was extrapolated to become the dual ECDRBG backdoor. Other than that, like, you know, what has been in there. But this slide is interesting because it makes it clear that they are able to decrypt VPNs, and in particular, ICE and ESP on a large scale. And in the same slide deck, they talk sort of in the same breath about TLS and about SSH. And when this was published, many people saw this and they said, well, okay, you need the ESP exchange. I don't know. You need the pre-shared key. They're using pre-shared keys. I guess they're just stealing keys out of sysadmins' emails and whatnot. So I don't know. That's how they work. But, okay, classified stuff is over. If you look at the IKE key exchange, this is one way that VPN traffic can be negotiated. This is a total cartoon, but the way that it looks like is, so if a client wants to negotiate with a server, Alice sends over a list of pre-chosen groups. There's a list of about 10 of these. Many of them are these Oakley groups that were generated in the 90s, 768, 1024 bits. There's a 1024-bit DSA group. And then there's a couple possible elliptic curve groups. But there's a very short list of groups of about 10. So Alice supports some number of these groups. Bob chooses one of these groups or says, hey, I don't support any of these groups, try again. And then they do a Diffie-Hellman key exchange. And then when they're actually doing the in order to transition to encrypted traffic, they both have a pre-shared key, and then they apply a PRF to the negotiated Diffie-Hellman secret and the pre-shared key, and they derive their shared secret, and then they move to symmetric encryption. So this is kind of what it looks like. So if the NSA, as they claim, is breaking VPN traffic on a large scale, they either need to have some kind of vulnerability in the symmetric traffic or something that's sent here, or they need to be both collecting the pre-shared key and somehow breaking this Diffie-Hellman key exchange. So either there's a symmetric break, there's some kind of protocol flaw that's offline, or they're breaking the Diffie-Hellman key exchange. And so if you sort of look at the pre-computation numbers, it's close enough that breaking the 768-bit and the 1024-bit groups that everybody is using, that is consistent with, if you've done that pre-computation, then that is consistent with being able to break the discrete log passively at will for not that much effort, and then being able to decrypt this traffic consistent with. If you look at, I lied. If you have a clearance, close your eyes again. So this is a picture of the infrastructure, the cryptanalytic infrastructure that is used to decrypt the VPN traffic. So they take the key exchange messages, they feed them into this specialized infrastructure that they have. They send the key exchange messages through a series of attack orchestrator, and then they eventually get to high-performance computing resources. And this is a database of known pre-shared keys. if the pre-shared key is known and whatever this high-performance computing resources come back with a success, then they are able to send back the decryption keys, and then the decrypted data goes into some databases. This is what their infrastructure for decrypting this stuff looks like. So the sort of big picture is they take this handshake, they send it to some big computers, they come back with the symmetric shared secret, and they decrypt everything. So if we hypothesize that it is possible to break a single 1024-bit prime to do one pre-computation that would take a few $100 million and 1 year, this would allow breaking 66% of traffic to 66% of all of the hosts on the internet that speak VPN traffic. And actually only doing the pre-computation for a single 1024-bit prime. So for SSH and IKE, these are the same prime. So if you've done that pre-computation for this 1024-bit prime, then you get 25% of SSH, you get traffic to 25% of SSH hosts for free. This is a different prime, but if you throw in having done that pre-computation for one more prime, then you get, say, 37% of all HTTPS traffic. These are numbers from internet-wide scans of how much traffic you could break if you could break all 512-bit primes, all 768-bit primes, one 1024 or 1024-bit primes. This is what, this is assuming passive collection. So this is what the servers want to negotiate with the most commonly used clients out there.
Question. My understanding of your percentages, so those are relative percentages, so percentage is 66%, of this percentage of VPN traffic. Do you have an estimate as to how much VPN traffic there is relative to HTTPS?
We're not the NSA. It would be wiretapping to get that number. Maybe some ISPs have it. But yeah, I don't know. I mean, there's a lot of corporate networks out there. And looking at sort of the intelligence applications, I mean, they're clearly interested in the traffic that's going over these corporate networks. So it may be that sort of as cryptographers and as security people, by focusing on HTTPS as like the application of cryptanalysis all the time, we've missed the really big, important target here, which people weren't really paying attention to, which is this protocol that has baked in a set of 10 prefixed groups, and where most of the clients prefer to speak using a single 1024-bit prime. So this is my last slide. I'm totally over time. So some practical mitigations. This is sort of in order of preference. I think, what do you do about this? Well, move to elliptic curve crypto. We don't have the same kind of pre-computation attacks for elliptic curves as we do for discrete log. You could say, okay, if elliptic curve crypto isn't an option, then switch, sorry, that should be 2048-bit primes, move to larger than 2048-bit primes, although I guess 2018-bit primes are also okay. And if 2048-bit primes aren't an option, then reusing the same 1024-bit primes is probably a bad idea, especially the one that people have been using for decades. And major browsers have been rolling out fixes. I think Apple just rolled out one this week, refusing to accept 512-bit groups, and they will be sunsetting 768 and 1024-bit soon. So I think for sort of a more theoretical audience, if you're thinking about what will lattice-based crypto look like in a couple of decades when you've won and it has become one of the most commonly used and deployed crypto systems out there, knowing what we know now about sort of the development of cryptographic parameters through the 80s and 90s, how would you standardize your constructions so that they can be secure for as long as possible? Do you negotiate parameters, or do you just say these are the one set of solid good parameters, nobody gets to change them ever? How do you protect against implementation mistakes? Because clearly the implementer needs to be considered as an adversary in our model. And also, how do you defend against politics? So how do you make sure that some malicious person on your standardization committee didn't actually manage to slip in a secret set of backdoored parameters against your will. So our paper is online at weekdh.org. There's instructions for sysadmins to change the baked-in primes and the parameters in many different kinds of software, and there's some videos, and you can watch us man in the middle and connections to lots of things. So thank you.
So I have a question about the export downgrade attack. So in the attack, it seems like it's a fairly crucial step that the man in the middle is able to make the client think that it's speaking DHE instead of DHE export. Do you have a sense of it? Is that necessary, or because I know it's like the client sends a list of cipher suites that it'll accept, right? Yeah. And then if it gets back just DHE export, is it a feature of the protocol that if DHE export wasn't in that original list, it aborts?
Yeah.
Oh, okay. So that's why you need the client to think that it's doing DHE.
Yeah. Yeah. If the server sends back like, hey, I'm going to speak this cipher suite that you totally didn't send me, then the client will say this is wrong.
One thing that I wonder about in terms of practical mitigations without moving to cryptography, which of course that's what people would do. But before the TLS breaks over the last few years, there was quite a few, maybe almost 10 years ago, there was this whole discussion about MQB and kind of sunsetting MQB and getting something that will provide forward secrecy for key exchange. So then there was the government standard, whatever it was, 800-56 or something like that, and IBM provided a lot of comments on that, and Microsoft provided a lot of comments, and my understanding was that most of the comments were ignored. They had to do with things like using HMQB instead of MQB, or Microsoft had proposals like Naxos or other things after that. And those would all essentially replace the usual, Diffie-Hellman with a version that had some forward secrecy. So I would think that would be another thing you could add to your list of practical mitigations. And I also wonder if you know if anything has been adopted in that direction.
I don't know of anything for TLS. I mean, maybe there's cipher suites, but I haven't seen them been negotiated by any clients that I use.
No, I don't think they were standardized in TLS. But
I'm not sure what other protocols might be using those things. I haven't been paying attention to the elliptic curve politics very much.
no, this is not elliptic.
Oh, it's not elliptic. Oh, it's.
Nothing to do with elliptic curves.
Oh.
I'm just talking about key exchange. So
Oh,
key
okay.
exchange that provides forward secrecy by instead of just having the usual static and ephemeral exponents, you also do something like a hash of the static and the ephemeral, or what the 800-56 called it, using a key derivation function.
Oh, okay. I haven't seen that be.
So it's a variation on Diffie-Hellman.
Okay. Yeah, I mean, I guess you could just say that all the servers should use actually ephemeral per connection exponents, which would seem to also sort of at least make some of these things better, but some do and some don't.
Okay, so there's a movie starting soon, so let's thank